Well, good afternoon and welcome to our on-farm solar PV training webinar series brought to you by the University of Maryland Extension through the Maryland Energy Extension Program. Today's topic is dealing with the integration of solar battery storage with solar PV. And I'll mention now before we kind of dive in that this is part 9 of an ongoing series. This program has started several weeks back, or back in September actually, and that we've touched on a number of interesting topics to date. If you were able to join any of those sessions, if not, the recordings are available on our Energy Extension page. That's extension.umd.edu/energy, and you can find the previous recordings. We've touched on many topics to date. We started back in September looking at the overall energy marketplace in Maryland, how solar fit in with that. We've looked at some of the design considerations, sizing requirements, and some of the policies and zoning ordinances, primarily from a on-farm use of energy, though from time to time we've addressed larger scale installations of solar PV, thinking of the solar farms and utility scale operations. But we've touched on a lot of interesting topics. Again, go to the website and you can find out more information from there. I welcome those back that have joined our previous sessions and look forward to meeting some of you in the future and some of our new attendees today. I hope everyone had a good Thanksgiving week. Last week, we took the week off from our weekly series for that last week, and it's, hopefully that was good for everyone under the circumstances. I know it was a little unusual this year, but we're back today looking at solar battery storage. As we get started today, we're still going to give some time for additional folks to join the program. I'll just start with an introduction for those of you that don't know. I'll be your host once again for today's session, as I have for our previous sessions. My name is Drew Chavot, and I'm an energy specialist with the University of Maryland Extension. I have a background in agricultural engineering, and I'm engaged in a number of applied research and educational programs related to on-farm energy use. With that said, we have a number of resources in that vein, whether you're interested in solar PV or energy conservation or other technologies on our website. The address is provided here. It's the same website that you have registered for this program on. We have a number of resources up there, not only for the agricultural sector, but for residential and other commercial operations as well. You'll find some resources on that website. Now, being that this is part 9, it's the last part of our fall series on solar PV. That doesn't mean we're going to stop doing programming like this. We're going to re-gear and retool based on the input and the feedback that we get on this program. We'll be putting some events on the calendar going into next year, calendar year 2021. It'll probably be a combination, if we're talking specifically about solar, will be a combination of online programming and education, a little bit more in depth in certain areas, depending on interest level that we get from folks like you and other stakeholders. But it could also be some in-person training, hands-on training as those restrictions allow. Going into next year. So be on the eye for that, on the lookout for that. Again, the extension umd.edu/energy page will have those events listed, or you can connect on social media or by the newsletter to find out about when those events go. But today we'll kind of wrap up this season dealing with on-farm solar PV. So let me give a few housekeeping notes as we get started. Number one, this is being recorded, as our previous sessions have as well. If you missed part of it or you want to review it, you can go on the website and record this video. It'll probably be up there by the end of the week. And as usual, the slide presentation and any other resources will be posted on the website to accompany that, so you can review that as you see fit. The question and answer section, you should have a Q&A feature at the bottom there. Please input your questions there as we go through the program, and I'll have take some time towards the end of our hour and address any questions that you have. If I don't have time, I'll try to follow up with you on that, or you do the same. You can reach out to me by email or by phone, and we can touch base in that way and get any questions that you might have answered on that. As we get started, let me launch the survey as I usually do to start the program. And this will kind of help us to understand your interest level. And this is anonymous, so I won't share it or anything. It's just good to have an idea of who's on the program today and your interest level. So you'll have 3 questions there. And then once you complete that survey, please click the submit button, and then we'll kind of dive into the program for today. So I'll give you a minute to do that. Okay, I'll give just a little bit more time. Make sure we collect all that we can here. And again, this information is valuable as we kind of get some events on the calendar going into January, February, and so on into next year. It'll help us to really refine what our scope is and what kind of programming we offer in the future on this topic. Okay, so about 10 more seconds and I'll close this up. I think we've got most responses by now, but if there's a few remaining, I'll leave it just for a minute. Okay, so I'm going to close that poll. I thank you for your input on that. With that said, let's take a look at some of the content that we'll be reviewing or learning through this session today. We're going to talk about quite a bit of content, and I won't be able to get into real specific nuts and bolts. We'll kind of leave that for question and answer time if you have really specific questions, but we'll start with kind of a basic overview of battery systems and the role that they play and different types of systems and how they can work. And we'll talk about the cost and financing for those systems. It is an additional cost, but it does have its benefits, and we'll see that as we go forward. And then towards the end of our program today, we'll get into more of the design analysis from an engineering and mathematical standpoint. So we'll kind of start off though with looking at the basics and kind of getting our feet wet in this topic of battery storage. So I'll start just by reviewing some of the system types we've seen previously. So this is a review to many of us who have participated in previous webinars of this series, but I'll start just by looking at the most simple system that you can have, and that's just connecting a solar module or a panel directly to a DC load, direct current load. And so in this example, it's just a submersible pump, a bilge pump connected to a panel. And what you'll see here is there's no additional energy delivery to the DC load. So you don't have a generator, you don't have a wind turbine, you don't have utility grid or anything. The only power source you have is that solar array. And so if that panel is not receiving sunlight, then your pump shuts off. And so you start to see, yes, there are some applications there, and it is used without any kind of energy storage. But if you integrate the energy storage, you start to see the benefit. Now at nighttime or when the sun is not shining on the panel, you still have some backup storage system. And so that's really what we're going to get into today. And so when we integrate a battery component, and this is kind of on the simplest sense, adding a battery into that system, it enables you to power the system once again, even when the sun is not shining. Now, it's not going to work indefinitely. Your battery will run out of capacity and you won't be able to supply energy anymore until it's reloaded. But that's kind of the idea, is that you benefit from that downtime when the sun is not shining. And there's an additional component added in here, what's called the charge controller. And we'll talk about that more specifically, the role that it plays, but it protects the battery, regulates the current and the voltage through the system, and protects the battery from being overcharged and some other facets that we'll talk about in terms of designing that. But that's a pretty simple system, is that charge controller and the battery system connected to it. And so that's where that fits in. On a larger system, what we might call an off-grid system, and in this case, it's just not tied to the utility grid. It could just as well be tied to the utility grid, but a similar example here, it just gets a little bit more robust, because we're not only talking about the DC load, direct current, but we're also talking about using an inverter to turn that DC electricity into alternating current. And we've talked about this concept in previous webinars as part of this series, but how that works is the PV module produces direct current electricity, and you have to invert that to alternating current, which is typically used in most commercial and residential applications. Whenever you plug into the wall, that's alternating current. And so in this example that I've shared here, I mean, you could do one or the other, DC load or AC load, but in this case, I'm sharing two examples. You have a DC load running off potentially the battery and the PV array, but you also have an AC load the energy is going through the inverter. But that's additional system there with the inverter cost and other components. And we've looked at the finances of that previously, but that's what the general idea of that concept is. If I get my mouse to work, I'll go on to the next slide. And this is a similar system, just a different way of looking at it. You might hear terminology like standalone system or battery-based system. In this particular example, what you'll see is 4 modules hooked in series, those modules being fed in through the charge controller to load energy onto the batteries, charge those batteries. In this case, there's no DC load indicated. It's just going through an inverter, and you're delivering that alternating current electricity to your main service panel. You can add an additional energy source. In this example, a generator is shown there. It could be a wind turbine or something else, but this is a basic system and where the batteries fit in with that as well. Now, there's 2 main ways that batteries are connected to a solar array and then to the electrical system in general. Those are the AC coupled and the DC coupled systems, and I'll kind of touch just momentarily on each of those. Starting with AC coupled system, you'll primarily see this with installations where perhaps you already had a solar installation in place. You had a solar array, whether it's rooftop or ground mounted, that was already in place, and maybe you're going back now and retrofitting it with grid storage, and we'll talk about the reasons you might want to do that. But in this case, there's some challenges by adding this battery capacity separately. For one, you're hiring a contractor 2 times to do the work, not only for the original solar array, but you have to bring a contractor back out to do the battery system. But even from an electricity standpoint, if you take a look at the diagram that I've shared for the AC coupled system, what's happening is you get that direct current generated from the solar module. It's being inverted into an alternating current where it can be used to power the loads. But then if you want to then integrate it into the battery storage system that's been added on to the system, you're going through additional battery-based inverter going back into direct current. So there's a lot of inversion happening between direct and alternating current, and it's back and forth. And then vice versa, when you want to pull that energy back from the battery, it's going from DC back to AC. So there's a lot of translation that happens there. And all that being said is you do lose quite a bit of efficiency by going back and forth like that. It's not saying that an AC coupled system doesn't have a viable role in a lot of applications. And really, if you do have a PV system already installed, it's likely not going to be beneficial to strip the whole system down and rewire it to fit a more conventional DC coupled system. You'll probably leave it like what you see in this top AC coupled system. So there's some trade-off there. It would be quite expensive and quite a headache to kind of strip everything down and start over. So you typically just add that system on, and we'll see kind of how that works moving forward. The other system is the DC coupled system, and that's a little bit more straightforward. Typically you see that with a system that's installed all at one time. And so we're going from a solar module. Direct current is pretty consistent throughout, and the only time that it's inverted to an alternating current is when it's ready to be used in its loading application, whether it's lights or fans or whatever it may be. And so we'll kind of leave it at that, and we can get into more detail moving forward. But I do want to share kind of what it looks like without the battery-based system. So I'll point out at this time we're probably no battery system is going to be able to supply 100% of your energy needs. It's not going to be able to supply all of your loads. So we'll start talking about how you kind of prioritize which loads are powered and which are not. But I just want to share this diagram with you so you get an idea of what a typical system might look like. And this is a grid tied system. You see the solar coming into one side of the diagram, and then that energy is being used in various ways, and it can be fed back onto the grid. We've talked about grid tied systems a number of times in our series, in this webinar series, but with net metering in Maryland, energy flow can go both ways. You can be producing energy and sending that to the grid, and vice versa. You can pull that back. Now, what happens with a grid outage is where it starts to get a little unique. If there's some kind of storm event, or for some reason the utility grid goes out, by law, your system shuts down at the alternating current level. And so, as I've mentioned previously in other webinars, when the utility line goes down, by law, you have to shut it down. And it's a safety issue that if you have any linemen out repairing that utility grid, you can't be sending electricity out onto that system. So as a result, you're losing all of that electricity at a local level as well. And so you don't have that electricity available. So again, that kind of indicates some of the priority in having some additional energy storage system, like what we're talking about today with batteries. You'll see the advantage to having that is you still have access to your load, even without posing a risk to the utility grid. And so there's many reasons that you might want to explore this from a resiliency standpoint. You don't want to lose production hours, or for your home, if you don't want to lose power in your home. There's reasons to incorporate that in, as well as emergency and disaster preparedness. But obviously with a battery system, it's an additional component, and not only is it the battery system itself, but it's the charge controller. If you have battery-based inverters and sub panels and other equipment, it's additional hardware and cost. It can be a little bit more difficult to maintain, depending on the type of system and the expense of that. So we'll kind of weigh out some of those options as we go forward. A little bit more detail on AC coupled system. Just the diagram here kind of indicates how it typically works. So when the grid is up, the new battery-based inverter, it has an internal transfer switch, and it's allowing your grid-tied inverter, your standard grid-tied inverter, the solar passes right through that, and it's connected to the grid just as usual. So that's where it kind of stands out the same. Now, what you'll see at the bottom is a little bit different than that standard system. We've integrated that battery bank system. We have a battery-based inverter, and in this case, we have a sub panel that's loaded with a few fuses for critical loads, and we'll talk about how we kind of prioritize that again. But again, you're not going to supply all of your energy needs with a battery system. You're going to pick out a few key things that you want to keep operational. And so this is how it kind of works when the grid is up and running. Again, if the grid is down for any reason, it's going to shut off. And so the new inverter, that battery-based, which disconnects the whole system from the grid and is drawing energy from the new battery bank to the critical loads panel. And so you're having all that power come through the critical loads and powering some of those individual systems there. DC coupled system is pretty similar, but instead of sending the whole output of the grid tied inverter to the battery based inverter, you leave it in the main breaker box. You take one of the DC strings of the solar array and send it through a switch to a charge controller to charge up the battery bank. And so you can take a look at what happens here when the grid is up. The switch is sending all of the solar power to the grid tied inverter. The new battery-based inverter chargers using that AC power to keep the battery bank charged up, so the pathway is through your grid-tied inverter, through your new battery-based inverter, and loading onto the battery. And so you're loading that alternating current. So again, you kind of get an idea how that works. Now, when the grid goes out, we'll take a look at what happens. Again, the grid shuts off everything on that right-hand side. The grid-tied inverter, in this case, disconnects itself from the grid, just like usual, and the battery-based inverter then powers up those critical loads from your battery bank. So the same kind of idea there, just different ways, a little bit different ways how it works. So that's kind of a general overview of how it works. We'll talk about some of the different types of batteries that are available on the market today. Just to highlight a few of the main ones, the main two categories that you'll see on the market are these lead acid batteries. Those are the traditional lower cost battery systems widely used for a variety of applications, including different solar applications. The lithium ion batteries, I'm sure most of you are familiar with Tesla and the other models as well. Those lithium ion batteries are much more efficient They do have a price tag to go with them, but they have a longer lifespan, and we'll talk about some of the other benefits of those as well. There's another technology is saltwater-based technology, and I'm not too familiar with this personally, but there is a growing market for these saltwater systems as well, kind of intermediary in terms of the expense and efficiency of these two systems. But for today's session, we're going to spend most of our time discussing lead acid and lithium ion as the two most common on the market. And there's many other types as well. And within this, we're going to kind of break down looking at this traditional lead acid. We're going to look at various technologies that are within that category. On the left-hand side is the flooded lead acid battery. It's the most traditional battery technology, but it has a few downsides associated with it. For one, there's a little bit more maintenance and care with the electrolytes, and they can be spilled, and you have to kind of balance those out. There's also the issue of hydrogen gas being generated that could be more of an issue in terms of combustion or anything like that. And so sometimes with additional cost of maintenance and insurance with transporting that, shipping and transportation of that, it could add some expense to it, but it is a widely used battery. More so what we'll see is these valve regulated systems. There's two in particular. I'll point out the AGM, it's absorbed glass mat, and the gel system. And I don't want to get into the details of the chemistry of these two batteries, but these are two common ones, and we'll touch on these going forward quite a bit as we look at some more practical examples. The AGM and the gel are two common batteries. Maintenance is pretty negligible in these systems in particular. They don't have a lifespan still as the lithium ion, but they're fairly reasonable, and they've been used widely in solar applications for a number of years. I've included kind of a rundown, and I'm not going to read through all these notes on the differences between battery types, but I've highlighted the three flooded, gel, and AGM. Those are all lead acid batteries, and then the lithium ion, again, the more efficient type. Just in a general sense, I'll kind of highlight some of the different aspects, but I will post this information on the website. So if you want to go back and review it as a resource later, you're welcome to do so. But I'll highlight a few aspects now. For one, the efficiency, but also, looking at the lifespan of these different technologies, the flooded, the gel, and the AGM, all those lead cycle, you're looking at just a number of years, less than 10 years typically for all of those technologies. Again, it's manufacturer specific and model specific to the battery that you're interested in. But in general, you'll see that the lithium ion typically has a lifespan that's much longer and a warranty to match that. Usually these batteries, lithium ion, for instance, will be typically warranted for about 10 years, but you'll probably get lifespan beyond that. With any battery, though, you're probably going to replace it before the other components of your system, before you replace the solar module. If it has 25-year warranty on the solar module, you're looking at a battery of, at best, with the lithium ion, only 15 years of use. So you'll probably have to replace it additionally, depending on how heavily it's used and other circumstances of its operation. The other aspect is with cycling, and I'll kind of describe what cycling means momentarily, but it essentially just means you're using the energy, the capacity in the battery, and then you're recharging it. And so that makes a cycle. Every time you use up the energy and then refill the battery, that's a cycle. And so you typically get more cycles with your lithium ion batteries in the range of 3,000 to 5,000, get in the hundreds typically for most of your lead acid batteries. Again, some warranties will kind of address this factor, but we'll kind of touch on that moving forward. Again, from the maintenance standpoint, really no moving parts. The only real maintenance that you'd have is with the flooded acid, as I mentioned previously. Again, I'm just going to kind of leave it at that, and we're going to move on, but you can revisit some of those topics if you're interested. In terms of the cycling, again, I want to highlight the importance here of different battery types when we're talking cycling. And that's, again, discharging the energy in the battery and then really refilling it. So, you think of a cell phone. As you use your cell phone during the day, you're going to deplete the energy and use up that energy. And then at least by the end of the day, you're probably going to have to recharge your battery. And that's a cycle. And so the batteries for your solar integrated system will work the same way. and depending on how many times you're running the cycle, you might deplete the battery before its lifespan is expected to end. And so you kind of see in this graph that I shared on the left-hand side, for this example, with a lithium battery, as shown in this example, if you are running 2,000 cycles, so that means you discharge it and recharge it 2,000 times, you'll start to see a decline in its capacity over time. And so after 2,000 cycles, it's not going to, that battery is not going to operate like it did on the first day. You're going to see a decline in its performance over time. And I'll also point out, you'll see a difference typically between the lithium ion batteries and those lead acid. In this example, it's showing the AGM batteries. You'll see a sharper decline in those systems compared to the lithium ion. So one advantage. And you kind of have to balance on a case-by-case basis if it's worth the investment in a lithium ion system for some of those benefits. Now, a similar term, and we'll use it as we get into some of the examples and calculations for designing a battery bank. I want to point out this term depth of discharge, which is how much energy capacity is just discharged as a percent. So as a general rule, lithium batteries are designed to be discharged between 80 to 90%. Let's say if it's a particular battery you're looking at is designed to discharge up to 90%. None of these will go to a full 100%. No battery that I'm aware of will be discharged that significantly. But a 90% discharge would then be a 10% state of charge. Those are inverse parameters. So 90% discharge would be 10% state of charge. We're not really going to use the term state of charge too much, just beyond that. But note that lithium will typically be in the range of 80 to 90% depth of discharge, whereas an AGM or a gel lead acid battery, for instance, will be 30 to 40%. They don't quite go as deeply discharged. If you do exceed that recommended level, you're going to end up degrading your battery quicker, and you'll have to replace it a lot sooner because of that. They're designed to meet that capacity. And like I said, there are other batteries out there. There's tables here for lead acid and different types of batteries and carbon. There's nickel batteries and other things like that. And we don't really have time to get into all those details today. Another parameter would be important, not only the power, but how long you want to be able to power the system would be implied in this term, days of autonomy. And so you're not going to be able to power a system indefinitely on batteries. 2 weeks would be pushing the boundaries of what's economically feasible, typically talking in several days range in terms of the days of autonomy. But again, this is a case-by-case basis on what your goals are and how you want to design the system and how much money you want to spend on the system. But we'll go through some different examples of days on autonomy. And I know I'm kind of nearing 1:30 now, so I'm gonna proceed, but we'll kind of come back to this idea of days on autonomy, and we'll see how it kind of factors in when we go through an example of a practical system design. But all these kind of parameters are kind of interrelated, and we'll get to that. Temperature also plays a role in the performance of a battery system, and as I said, this example here has some nickel batteries indicated. We're not going to really spend much time on that. What I do want to point out is kind of general trend between lithium ion and lead acid. The lithium batteries, and again, this is a manufacturer and model specific information, but typically those lithium ones operate over a wider range of temperatures. And so you can have more flexibility in where you store those batteries. In some cases, the lithium ones might actually be, you might be able to install those somewhere outside because they are more resilient in their temperature range. Lead acid batteries are typically more sensitive, some batteries more than others, but you have a narrow range. And so you're going to have to be a little bit more careful where you position the battery system, especially with the lead acid. And those are typically in a garage or a basement environment where you have a more controlled environment. For instance, if you take a look at this graph on the top right side, you'll see at higher temperatures, you start to see that lifespan of the battery impacted adversely. And so if you are operating the battery at a high temperature, for instance, you're not going to get that great of a duration out of the system. Excuse me. So to kind of shift gears and talk a little bit about the economics before we get into an actual system design, I'll start just by saying there's no direct revenue stream associated. There's no direct revenue stream associated with the battery system. I do see a comment that I'm fading in and out. I hope everyone can hear me. If there's still problems with the microphone, let me know and I'll try to address that. Just note in the Q&A if there's any problems hearing me. I'll try to speak into the microphone though. But I'll say related to the economics, there's no direct monetary value coming in. There's no revenue stream coming in from the battery. It's not like you're selling solar renewable credits or some of that net metering that we've talked about before. This is more of a local level benefit to have energy on hand. But I will mention for agricultural operations or other commercial businesses where you have a peak demand charge or advanced utility rate, maybe you're charged higher at a different time of day. There is some indirect benefit where you might want to store the energy on a battery. And if your utility at the time of day when your utility is providing, charging more money for that electricity, you could be using that battery energy. And so that's kind of what this diagram is showing. Have that energy stored in the battery and on hand for when you want to use that. And you could use that shift that energy use from the batteries to a more productive period of time when you're being charged a higher rate from your utility provider. So there is an economic side to that. You just kind of have to weigh, is it worth the expense of a battery system for you to avoid some of those higher rates? And again, that's case by case basis. Utility outages are a big concern as well for many of us. I would say more so than for some in a residential sector. When you're talking about business and agricultural, you're talking production as well. Beyond just a headache, you could potentially put this utility outage to in terms of the economics. If you don't have power, if your utility line is down and you don't have power, then that kind of stops your operation as well. So I'll say there could be an economic side of that. I don't have real contemporary data on this, but I'm reaching back into the early 2000s to share this information. These are from two different studies, kind of putting that utility outage to an economic standpoint. So they've shown that even for a momentary electricity outage from the utility provider, it's still costing in our area, in Maryland and South Atlantic area, it's costing even for a momentary outage over $600 for some commercial operations. Now, again, that's not every farm is going to be impacted to that extent, but similar result from the same timeline. And again, this data is quite outdated, but it does show there could be an economic stance to economic basis to stand on here. But for the agriculture, this first line shows that for an hour of utility outage, it could cost a farm upwards of $1,000 or more just in lost production hour and production time. So again, you kind of have to assess that on a case-by-case basis, but there could be some benefit there. Now, I think most of us are probably kind of wanting to know what the cost of the system is, and it's highly variable depending on the type of battery and the type of system. We've talked about AC and DC coupled. Are you talking about off-grid or on-grid? And other factors piece into that, but there's some general guidelines provided here. I'm not going to get into too much detail on that. What I will say is that hardware costs, the battery system itself typically cost about 55% or more of the system overall. The other soft cost and installation included there. I have highlighted a couple prominent models on the marketplace today. I think, as I said, many of you are familiar with Tesla. The Tesla Powerwall 2, for instance, it's a rather expensive lithium ion option, could be upwards of $10,000 or more. Does have a pretty good capacity, energy capacity in 14 kilowatt hours. And again, with the lithium ion batteries are typically about 10-year warranties. They could also have the stipulation on how many cycles it's rated for. So be on the lookout for that as well. But I wanted to kind of highlight the difference here in terms of the warranty for some of these AGM lead acid. So the lifespan for the lead acid are lower and the warranties are lower to match that. typically, around 3 to 4 on average, but I've kind of shared 2 examples here for different warranties. But in either case, you're probably going to have to replace these lead acid before you replace a lithium ion. So that's definitely a piece of the puzzle to consider. In terms of financing these, we talked about, we had a session a few weeks ago on economics and financing for PV systems. So you can go back and excuse me, review that previous session on financing for more details, but I've included 2 of the tax credits here for more detail. So at the federal level, you have with the IRS, you have that federal tax incentive tax credit. And in this case, you have to have 100% of your system 100% from solar charging. At the commercial level, you could go down to 75% and you can get a portion of that tax credit. Now, I'll kind of point out we're kind of at the transition here. It's at the end of this year, the 26% is going to be bumped down to 22% going into next year. And so you're really running out of time for that 26%, and then it'll go down to 10% tax credit for the federal tax credit in 2022. For residential, it'll be phased out completely after that. For commercial, including our agricultural sector, we could remain at that 10% indefinitely, as far as I'm aware. The other tax credit is a state level. It's a program operated by the Maryland Energy Administration. This is the Maryland Energy Storage Income Tax Credit, 30% stacks and income tax credit. For a commercial system, it's up to $150,000 maximum. For a residential, it's a $5,000 max. So you can take advantage of some of those tax credits. I do want to highlight this example I've included here. This is Dog's Day Farm in Gaithersburg. And it kind of indicates the benefits of coupling different financial incentives, rebates, grants, and tax credits together. And so, in this example, they've used a clean energy rebate for $5,500, as well as the storage rebate for $12,600. So combining those different rebates and as well as the tax credits that I've just discussed, that's where you're going to really start to see the benefit to the system, is bringing that cost of the system down and then gaining the benefits from having it. So that's kind of a broad overview of battery systems and how they work. I'll briefly kind of get into how you design a battery bank system to meet your needs. And if we have time, we'll kind of towards the end, we'll touch on charge controllers and some of the other components in designing of the system. So as I mentioned previously, you're not going to be able to power every load that you have. You're going to be identifying a couple key systems that you want to operate, usually tying in less than 10 things onto your sub panel on what's absolutely important for you to keep running. And I'm not going to tell you what's important, what's not. You will know for your case what's important and what you need to keep running. I will highlight that some of the challenges and what I mean by non-critical is just things that are going to be challenging in order to run off a battery system. That's going to be your larger power consumers, your central HVAC system, or any compressor system that might have a large surge of power at the startup. Those are going to be a little bit more challenging. Typically talking about, smaller fans, lighting systems, and other things that can be run. And again, it's going to depend on your system and the way that you design it. And it's going to depend on your days of autonomy and some of the other factors. Now, what I have done in the past, I've shared a number of resources on how to collect data on energy use. This is kind of a similar system. I've copied a spreadsheet here. It's a spreadsheet developed by AEE Solar. I've included a link on the slideshow. So if you wanted to use this particular spreadsheet, you could do that if you're interested in that. But what I started to do is just for the example that we'll do in this webinar, is identifying a couple key loads that I want to maintain, and I'll design a system around that. And so, I won't go through each and every detail, but I've included many AC alternating current electricity systems. There's a lighting system, and I put in 52 watts for that. If I use the lights for 5 hours a day, then I can do the math on that. For this example, I've also included DC lights as well, just to give an example as we go through this example of how you would work with DC and AC at the same time. But you could have a DC lighting system or other DC system operating off that same system. So I've put all these critical loads, things that I want to manage, and the total for me in this example is 2,191 watt hours of energy each day. Okay, and so that's one way of kind of assessing is you can use a spreadsheet like that and start to take notes and identify what's important to you. Just as a recap of the difference between power and energy, and we've touched on this a number of times previously, but power is different than energy. I'll just briefly share this example with you, and I've shared it previously as well, but a 100 watt light bulb, that indicates what the power of the light bulb is. That power rating is usually stamped on the light bulb itself. It's 100 watts. If you were to use that light bulb for 3 hours, you multiply the numbers together and you get 300 watt hours of energy. So units of watt hours or kilowatt hours, that is a unit of energy. And you think about this in terms of an analogy here of a water container. The larger that container is, the more capacity it has and the more full of water, or in our terms, we're going to speak of that as electricity or energy. So it has a larger capacity and it's going to take longer to deplete that resource. We've also touched on how power relates to voltage and current previously. And just as a review of that, we'll look at this particular solar module is a Kyocera brand PV module. In this case, the power of the module, if you look at the back of the solar module, it says 140 volts. 140 watts. Let me make that clear. 140 watts is the power of that module. Now we can check their math on that like we've done previously. We can use the voltage and the current that they provide, or we can measure that with a voltmeter if we're interested in that. But checking the math on that is 17.7 for volts times 791 for the current. Sure enough, it equals 140 watts for the power of the solar module. Now, I do want to make a couple distinctions here regarding nominal voltage, and this is a term you'll hear me use moving forward. And as you explore some of the options that you might have at hand, you'll kind of hear this term nominal voltage thrown around. What I will say, it's essentially nominal voltage. It's a way to categorize battery-based solar equipment. Because a higher voltage is needed to charge the battery, nominal voltages are kind of used to help see what equipment goes with what. And so, in this example of the Kyocera model that we're looking at, it's a nominal 12 volt module. So the actual voltage is much higher, and you see 17.7 for the voltage at maximum power, and the voltage open circuit is 22 volts. So it's actually a little bit different than the nominal voltage. A panel designed to charge a 24 volt battery bank, for instance, will have a voltage of around 44 volts and a VMP of 36 volts. So whenever we're talking about nominal voltage, we're not talking about the actual voltage coming out of the module or the battery itself. We're talking about that basic category. So, an example, if you wire two 24 volt batteries, two 24 volt panels together, or you could do 4 of the 12 volts together, that'd give you the same thing. But let's say we're putting 2 of these 24 volt panels together in series, then we could charge a 48 volt battery bank with that. By having 2 panels in series, 24 volt and 24 volt, that would tie in well with a 48 volt battery. So this was kind of the basis, particularly with off-grid systems, and before we saw more of the grid-tied systems come online. But to a large extent, the industry has kind of standardized the 60 cell system, 20 volt system. This in particular is not high enough. The 20 volt is not high enough to charge a 12 volt system, or it's not a large enough voltage for the 20 volt battery. but we'll kind of get some ideas as how we compensate for some of these design parameters moving forward. Okay, so the first thing when we're talking about designing a system, battery-based system, we need to decide what voltage we're going to have the battery bank at. So for most off-grid systems, designing the battery bank, you can, as I've put in some of the questions here, mostly you're going to have either 12, 24, or 48 volt battery bank. The questions here will kind of help you refine what you're looking to do. But what are your load voltages? If you have, for instance, a 12 volt battery, a 12 volt light, then you're going to tie that in with a 12 volt battery. Or if you have a pump that's 24 volts, you can easily tie that in with a 24 volt battery system. If you're using an inverter, a smaller inverter like 2000 watt inverter might be best for the 24 volt battery bank. If you have a larger inverter, 6000 watts, you're probably going to go up to 48 volt battery bank. So it could be dependent on that. It just depends on what kind of system you have. Question about the distance between the array and the battery. And I bring this up because I've seen a number of times where your solar array is actually pretty far from where the batteries are situated. So I've seen, when you put arrays maybe way back in your backyard, and then you have the battery system in your garage, there's quite a bit of distance to cover in that case. And in some instances, what you might want to do is consider, should you bump the voltage up? And as a result of bumping the voltage up, you're going to get a lower current, and you can get away with smaller gauge copper wire. And so if you're covering long distances with your copper wire and conduit, you might be able to save some money with a smaller gauge wire, and that might justify the higher voltages. That's just something to consider there. And then I'll also say when you're talking about having 3 or 4 parallel strings, that's when we start to get some uneven charging and discharging on the battery. So we typically want to limit, depending on what kind of solar PV system we have, what kind of battery system we employ there. And so I'll go over just a brief example here of how this might look. But with a battery I've picked out here, this is a 12 volt and capacity of 200 amp hours. When you multiply the volts and amp hours together, you'll get what the energy is, 2400 watt hours. And so that's the example for this battery. A lot of batteries, most batteries, in fact, will have that watt hour listed on there, but you can do the math yourself. If you connect two of these batteries in parallel, and so positive to positive, negative to negative, these batteries in parallel, you're increasing the amp hour rating on the battery. So now we're going up to 4,800 watt hours. You could do these in parallel 4 batteries. Again, you might have some uneven discharging and charging. You might not get as great battery longevity out of that, but this would be one way to increase up to 9,600 watt hours. Now, if you wanted to do 9,600 watt hours, another way to do that would be do 2 in parallel, 2 series in parallel, and each series has 2 batteries in it. So a different way of connecting that. In this case, now we're increasing the voltage to 24 volts and 400 amp hours. So it's a different way of doing that. And again, you can hook a series here, increasing the voltage of this. Remember, we're starting with just a 12 volt battery, but we're increasing the voltage now to 48 volts and 200 amp hours remains the same. So different ways of doing that. Quick example of this in practice. Let's say we have, if we need to have 9,600 watt hours of energy, just like in the previous example, but you need a 12 volt battery bank for your loads. So you can accomplish this, again, doing 2 in parallel and 2 in series, 2 parallel series of 2 batteries, if that makes sense. You just need to pick a lower voltage. So in this example, I'm going to use a 6 volt battery. And so when you wire those in 2 parallel series, two parallel strings of 2 batteries in series, you get that 6 volt batteries in series makes 12 volts. And then the 2 405 amp hours add up to 810 amp hours. If you multiply that together, you're getting 9,720 watt hours. And so you're meeting your needs by wiring it that way. So that's just one example, but I I will give a quick example here of how you can design a system from the ground up. So we're going to take a look at starting at step 1, really not working with the battery system yet, but just assessing our energy use. And this goes back to that table I shared earlier, looking at critical loads. So I'm going to stick with that same example that I shared earlier. I have an AC load totaling 2,148 watt hours. I have a DC load just for a simple lighting system of 44 watt hours. In this case, to determine how much energy use I have, I'm going to put my DC and add that to the AC load. Now, one additional factor, I'm compensating for the efficiency of the inverter. Remember, no machine is 100% efficient, and that applies to the inverter as well. So, you know, that's the only efficiency I'm really accounting for in this case, is that of the inverter, and that's only applied to the AC portion of that load. So that's why I separated those out. So if I take, you know, 44 watt hours and add it to the AC component, I have an energy use of 2,379 watt hours, and that is what we're going to design the battery bank to deliver that energy. And so we're going to look at it from 2 standpoints. We're going to look at it from the watt hour capacity as well as the amp hour capacity. And so we'll start with step 2 here, looking at the watt hour capacity. I'm going to start with the energy that we just calculated, the energy use that we calculated. For this example, I'm going to put 3 days of autonomy in. I'm also going to include a temperature multiplier for temperature, much like what we're having today, around 50 degrees. And that comes from this multiplier term here. Again, it's going to be different for different types of systems, depending on the manufacturer of your system. But here I've got a multiplier of 1.19 for 50 degrees temperature. Again, temperature impacts the performance of these systems. So I'm going to put that correction factor into the equation, and I'm going to put in a depth of discharge of 50%. In this case, I get a capacity of 16,000, almost 17,000 watt hours. So that's the first key parameter. Also going to look at this in terms of the amp hour. And if you get lost in the math, don't worry, I can help you offline, or you can kind of use this. And this is just a real basic example. It's not real robust, but you can review this later if you're interested. But the amp hours here, I'm just taking that watt hour capacity, dividing by, in this example, we're going to use a 48 volt battery bank, and that gives me 354 amp hours. Okay, so to kind of complete this and to select a battery, we're going to do a couple things. Take that amp hours that we just calculated, 354 amp hours. You're going to divide that by the maximum number of strings that we want to use. So we're going to go with 2 strings in this example. So that says that we need 177 amp hours for each string. And you can pick some batteries based on that. I've picked this battery in particular. It's a 6 volt lead acid battery, 190 amp hours. And so we're at 190 amp hours. That meets our needs there. But to get an idea of how many batteries we need, we'll go into step 5 and 6. And so we'll take our voltage divided by the voltage of the battery. So that's the battery, the system voltage, 48 volts, divided by the battery voltage. That shows that we need 8 batteries for each string in the PV system. And we have 2 strings. So 2 times 8, we're going to need 16 batteries total. So again, I kind of ran through that example, but it'll be made available online if you're interested in doing that and exploring more details. And hopefully this example will kind of help you move forward. So I know we're kind of low on time. Let me I'll just say a couple notes about charge controllers for those of you that might be interested in that. We won't get into too much detail on it, just so I have time to get to any questions. Remember to put those in there. But where a charge controller fits is between the module and the battery. And so this charge controller does 2 things. It protects the battery from being overcharged. And so it'll regulate current and voltage. And it'll prevent discharge during nighttime, for example, if you had voltage going from a higher voltage being backfed or something like that. So that's a critical component there. There's a variety of different systems on the market. You see PWM is the pulse width modulated, as well as the MPPT. And I don't want to get into the details real specific how these work, but I'll highlight some of the key differences. MPPT has quite a bit of advantages because it increases the current of your system. We'll kind of look at how that works. They both kind of charge a little bit differently depending on what state of charge the battery is in. But I'll just kind of highlight some of the unique aspects here. Look at some examples. So with the first type of charge controller, it's going to match the voltage of the module to the voltage of the battery. So 12-volt module would connect to the 12-volt battery. And you can say if we connected those in series, it's 24 volts on the module side and 24 volts on the battery side. So same idea though, you're matching the voltage in to the voltage out. I've included some examples there. I don't have time to get into that. I do want to point towards some of the benefit of an MPPT, but we'll start by looking at what happens with a PWM charge controller. So this is the first type of charge controller we'll talk about. The PWM, the voltage from the module, it starts at 18 volts in this example, and it drops down to 13 volts that the battery is operating at. And so in this case, what we end up with, based on that voltage being dropped to 13 volts, and at that current level, we have power of the battery at 72 watts. Now, some of the challenge becomes if you do not match the battery with the module itself. So in this case, we have a 24 volt nominal module. It's not matched with the battery. And what happens with the PWM again, the voltage in this case is starting at 36 volts. It's dropped down to 13 volts. As a result, we're losing quite a bit of power. So a lot of that voltage is shed. Excess voltage is lost and power is lost there. And so that's some of the challenge there. You really do have to pair those systems together. MPPT works a little bit different. I'll just briefly say you're matching the power of the systems from the module to the battery. It's matching the power by bumping the current up in proportion to the voltage drop. So the voltage drops, the current goes up. I just want to share an example of what happens in that case with an MPPT. So in this case, if we go with a higher voltage module and a lower battery, it compensates, the MPPT compensates for this by increasing the current. And so the current, regardless of what type of module you're using, you're going to get the same power. So you're able to use all 100 watts of the power of the 24 volt panel in this case. And so you see the benefits there in terms of the MPPT controller. Again, there's some additional examples that I'll include in this in the resources posted. This slideshow will go up. So if you wanted to work through some of these examples, and this particular example will help you size the charge controller based on the amp, whether you're looking at a PWM or an MPPT, you could size it like that. So I want to correct that there, MPPT. You want to design it that way, and you can kind of weigh the costs and benefits of that. With that said, we're going to move forward and close this out here in a minute. I'm going to start to take a look at questions as you roll those in. I do want to launch this final survey if I can.